live. Wow. And we're here. Amazing. Welcome, everyone. What do I do? What do I do? First of all, let's get you guys invited and online. Um, Let me know if you can hear me. Amazing. Let's pop out the chat. Pop out the chat. How do I pop out chat? Pop out chat. Let's minimize that. Minimize that. How about there? Minimize that. Okay, cool. Hey everyone. So welcome to another session this morning with Zach. And today we're going to go through something I'm really excited about, something I've been working on. Um, well, I've just started working on. I have been working on, what is it? libmpix. So I have a kind of a small project right now. Objective of the project right now is to add color correction to an ISP. And so uh, previously I've had um, in-book or theoretical exposure to ISPs. Well, in ISP now, when I'm talking about ISP now, I'm referring to image signal processors. So I've read about this in books. I've read the theory of how implementing this, and but I've never taken the time to go through an implementation of an image signal processor. Usually, I would try with some sort of digital signal processor for sensors or something. However, this time I ended up working on libmpix, and I have a project right now, and the project right now is to add color correction to libmpix, which is an image signal processor. So I thought it would be a fun exercise to just walk through how image signal processors are done, uh, partly in an effort to see, to try and understand them better, and also in an effort to kind of show how how much low level code is used and how it's used and where it's used and kind of like what you can do with these things and where to start and where to go. So, what we're going to really do today is just really explore what an image signal processor does and where to get started with them, and some examples of them, and so on and so forth. So, the the first um, the first sort of thing we can kind of look at is a few examples of image signal processors. So, or rather, let's go through typical definition of an image signal processor. So let me pull that up. Image in image signal processing. So it's image signal processing flow. Just so you can understand, just so we can understand what an image processor does and where. So I don't want to see one. I'd like to see the jobs. Mm, is it here? Can I get a flow chart here, maybe? Yeah. So essentially, what happens is um, whenever you use a camera, like let's say a digital camera or yeah, a digital camera. This is better for us right now. Whenever you use a digital camera, what you have is an array of sensors, and this array of sensors will most likely collect information in one. So you could either have something that does a linear that does linear image sensing, or you could have something that does, which means it just goes row by row, or you could have something that does frame image sensing, which means it captures the whole image one frame at a time. So, and one frame at a time means a number of rows by a number of columns. Um, in regardless of which one you have, either what you end up with is capturing an array or a list or a buffer of electrical signals, and basically you're just measuring voltages. Um, you Most image sensors will return a level of voltage um, depending on the pixel that they're in. So let's look at something like, yeah, where's my mouse? So let's look at something like this. What your camera is going to do. So this is just, I want to just look at the capturing. So this is, let's say, it would go through each pixel collecting um, a voltage for that pixel. Well, technically, it doesn't go through each pixel. It rather goes through each third of a pixel, because each pixel in reality, whenever you do color images, each pixel in reality is RGB, and and each of the colors is going to be an usually an 8-bit byte. So so each pixel is going to contain 3 bytes. One byte for the red, 1 byte for the green, 1 byte for the blue. And most of this is comes from the Bayer filter, which is kind of our current state-of-the-art way of capturing images. And what the Bayer filter has is a way of it's a it's basically a bunch of filters, a red, green, and a blue filters. This used to be canonically it was red, green, and blue, but now I think there's a cyan, magenta, and violet one, or cyan, magenta, and yellow one, CMY. But it's the same thing basically. The reason we didn't have a CMY filter in whenever this was being invented is that the dyes for cyan and magenta and yellow were difficult or unavailable to attain. Okay, cool. So what does a Bayer filter do? So basically, the process can be seen in this images. So the Bayer filter will have an array of, it will be a range with half of it being green and half of it being, a quarter of it being blue and a quarter of it being red. And this is because human eyes are very sensitive to green, basically. But you can find out more about this in biology and such. But the whole essence is that we have a bunch of filters, and then this bunch of filters goes through rows and columns. But for simplicity, you can assume an image, or rather, the data you're getting to be an image from an image to be a simply a large one-dimensional array. Um, I'll check questions if there's any questions first before I go on. Cool. So what image sensors will do is they will capture um, an array of information, and this array of information will be composed of bytes, and the bytes will be grouped in threes, and each three group of bytes will be red, green, and blue, and this red, green, and blue will come from the filters, such as the one I'm showing right now. Well, the most common one, or the ubiquitous one, is the Bayer filter. Although there's more, there's a zero one. I know there's a few more. Let's look down here. There's a few more. So there's the Fujifilm X transfer. There's the Fujifilm EXR, and then there's also the um, quad Bayer filter. However, this is just variations of this Bayer filter. What the sensor is going through is it's going through the set that is in front of it, and according to each pixel, depending on how many, we hear of megapixels, so they usually have a width and a height. Depending on how many pixels you have for the width and how many pixels you have for the height, it's going through the image, and it's sensing basically each line at a time. And then you have a horizontal sync, and you have a so you have a H H sync and V sync in image senses. So you have triggers, you know, you have triggers in uh, so that the image will be captured line by line, but every time a line is captured, you'll have a trigger, which is I think that is a horizontal sync. Yeah. So a horizontal, it'll give you a head sync every time a line is captured, and then when you're done capturing a whole frame, so if you have say a 16 by 16, a camera that can do 16 pixels wide and 16 pixels um, deep or down, you'll capture every time you capture 16 pixels in a row, you'll get a head sync, and then every time you go 16 lines down, you'll get a V sync, and thereby you'll have attained some triangle or square, which is actually what is a frame. Now, a frame in raw data is composed of bytes, and the number of bytes will depend on the width and height. So if you have a frame that is 16 pixels wide and then 16 pixels long, what that means is you have 16 by 16, which is going to be something like 256, I think. Uh, I'm pretty sure 16 by 16 is 256. So let's do that. 16, oh, 16 times 16, 256. Cool. But remember, so this is the number of pixels. Okay. However, remember each pixel is 3 bytes. So times 3, which makes it 768 bytes. This is just the number of bytes. If you think about it, if you have one one-dimensional array that is 768 bytes, you can chunk it so that you have pixels. And then you can chunk it so that you have pixels, and you can chunk it so that you have image rows. And that means if you can chunk it into pixels and rows, first of all, into rows, you have an image, so you have a frame, you have lines in a frame. And then within each line, you can chunk it into pixels in the line. And so the what an image signal processor does is it consumes this one-dimensional array, and then it consumes this one-dimensional array, and then it will perform these steps that are listed here. So the number one is this is the original scene, as you can see here, the scene, the set that is in front of the camera. And then what you can see, number two, is this is now the frame that has been captured from the image sensor, and it's been captured in, say, gray. Okay, just one color. This is just before you add colorization, before you do anything. This is the raw frame as captured from the sensor, and we will do this almost practically just now. We have to explain. Um, let's 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 start here. So we have a row, image here, and the raw image, um, open raw buffer online. Is there something that can open this thing online for me? Let's start. Mm, okay. I just want to open a row buffer. row buffer. Anyways, let me show you. So what we have here is uh, 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 um, a row, such a row frame that we've gotten. This is just the bytes in a frame. And I think the size of this byte is something like um, 800 by, it's from a HiMax sensor. So it's 800 by 765, if I'm correct. So I think we can do mpix, uh, mpix read frame, frame, and then we can do 700, but I mean, let's do 800 by, I think, 640, and then let's read it in gray, and then I probably need to convert this into some sort of I need to convert this into some sort of RGB. Let's actually do. I remember it's 750. 750. Let's make it view. Let's convert it into some sort of RGB 24 so that I have all the pixels, and then let's do QOI. Let's encode it into some file that we can understand, and then let's write new, new stage stage one dot QOI. So let's make that. I think that should work. Ah, this is the time. Okay, so that should work. LS. So we have stage one dot QOI, and then we can do. I think I have this is an SFM peg. Yeah, yeah. Let's do stage one dot QOI, and then let's do stage one dot PNG. Awesome. Let's clear. So LS again. So people see. So what have we done now? We've gone from a row buffer that we're getting from a sensor, and then using this row buffer that we're getting from a sensor, we've encoded it into a QOI image. And the reason we encode it into QOI is because encoding into JPEG or encoding into PNG is quite resource intensive, and hence it's much easier to let me get you to the documentation. Much easier to just go straight to QI, and then you can use that for. Wait, huh? Wait, just a moment. You can, yeah, you can Q once you encoding in Q is in QI is much lighter and much faster and not very intensive for your CPU. And then you can use a tool like FFmpeg to convert from QI into PNG, something that you can observe. So if we go into the, if we go into the, if we go into our, if we go into our temp directory and we look at our stage one.png, we have basically an image. This is from the row buffer that we process, and this is stage one. So you basically just accepted it, you encoded it into a format that you can have an image open on your computer, and then now we have that image open. Now, what is the next step? once 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 we have an image like this from a camera, bear in mind it's not that straightforward. So in for me to encode it like this, usually for me to do an encode like such, it's not that straightforward. Usually you would need you need the row buffer, and then you need to know to know the pixel size of the image, and then after that, once you know it, you can now like go to gray and then convert to RGB, which gives us pixels, and then once you have pixels, you see this this stage gives us basically a gray image. But image openers on your computer work with pixels, so you have to convert from the from the from the gray image into an RGB24 uh, um, an RGB format, and the RGB format is further explained here. I think how to convert pixel format. Basically, you want to go from a pixel format that your computer just understands, and then to a pixel format that uh, um, an image open on your computer can use. Fine, that is the beginning. And then once we've done this, once we've done an image from a row buffer, the next thing we need to do with once we've encoded it into one image like this, I think the next thing we want to do is to add color into this image, basically. And to add color into this image, so this is just like now adding color into the image. So what we have here, basically, what we have here is the first stage of the image signal processing, basically here, if you remember from the Bayer filter. We started with a raw file. So this is the scene that we want to achieve. So we started with a raw output, and we from that raw output we constructed it into pixels, which is number two. So you see, number two is just output of like an 800 by 750 pixel sensor with a Bayer filter. We just added a Bayer filter on top of the data that we have, and that Bayer filter constructed an image for us. Okay, so now in order for us to see the in order for us to see the colors into in order for us to see the colors in the image, what we need to do is now we need to uh, go through, and I'm trying to remember correctly what the nomenclature of this is. What we need to do is go through and do something called debayer. What is debayer? This is the process described here in Timo's icon. But basically, you walk through the image, and then as you walk through the image, you interpolate the color value of the pixels because you know how the pixels are arranged. So you know RGB, RGB, RGB. You're getting these tuples, RGB, 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 RGB. So you need to go through all the pixels, and you need to convert them into basically into a colored image, if I might say so. So let's and the way you do this is you need to read the source as a list of pixels. In this example, we just read it as a list of we just read it as a raw Bayer, like it has a filter, but we haven't processed it to show us any colors. Okay, so let's try and do that. The first thing we need to do is we need to use a raw format that will be accepted. That's our GGGP. And basically, here it is. Here it is. Yeah, blah, blah. Here it is. Supported operations, supported formats. Somewhere. yeah, format.h. So you need to go through and collect a format that you can, you need to read your raw data into a format that you can convert into colors. So here we see. So the format I'm going to use is sRGB, and it's somewhere here. So just I'm gonna find it. You can come back later and you can find it, but there's sRGB somewhere here. Mhm. sRGB. Yeah, here. Bayer format. So remember, just reading, you need to read it in a format that you can later use. So the first Bayer format that we're going to use is sRGB, and that this is among the number of formats that you can use. So read it in Bayer format. Cool. Let's read it in a Bayer format, and then we convert it to an RGB24 first. Well, we don't even need to do that probably because we can just go straight to something we can encode. So let's, and then we need to debayer. Debayer is demosaicing. So we can debayer, and then we can do that, and then let's see. Let's do stage two. Stage debayer. Cool. Hmm? So RGB 8. Okay. Okay. Oh. You can come. Okay, if you want. So it's RGB, I think 8. Let's do that. Oh, wow. And then we can do F advantage. Let's do that. Let's do stage debayer. UI to stage debayer PNG. Yes. Hello. Amazing. Stage debayer PNG. So let's see what we have. Stage debayer PNG. Amazing. So we basically went from raw to this, and now we're in here. So our the program we are using is consuming is processing the data that way. From raw, it processes the raw data. Now it's processed the raw data. Now it's going to into some black and white, well, gray, and then now we've made it to this, which is we've done a debayer, which is called a demosaicing, if you want to go for the academic term of it. Demosaicing can be found there. And that's the process of going through all the pixels and adding color information into each pixel. Because now, if you have a pixel, remember, if you have all these pixels and you know they are arranged in red, green, blue, red, green, blue, red, green, blue. So you can go and read those values as individual colors. And once you read those values as individual colors, you can now use those colors to basically construct the combined color of all the pixels. Um, However, one of the things that you end up on is usually whenever you do this, as we can see here, you end up in a place where the image is not um, what you expect. For example, we can see colors in this image. We can clearly see there's a human holding this, and there's another human in the corner, and there's some fluorescent light, and there's some boxes and some reflections. However, this is usually not how things look. So when you have an image like this, you want to pass it through, you want to basically tune it. You want to tune the image. You want to tune the processor so that it can, um, you want to tune the processor, the signal, the software that is doing the processing so that it applies the correct balances uh, so that you can basically get the right image out of it. And basically, what you want to do is you want to adjust the uh, greens and the blues and the so that you come closer towards an image. And the operation we can you do for that is, you see, so there's some white. You see the whites are yellow. So this is kind of yellow. This is kind of yellow. This is kind of yellow. This also looks to be white. This white here is yellowish, and everything is kind of yellow. So what we want to do is basically what is called a white balance. And I think this is in correction, documentation, correct image. So there's going to be, yeah, you need to apply some sort of correction. And this is, now we're practically walking through what an image processor does. So let's apply some sort of white balance and see what that does. So white balance is how we adjust the whiteness, okay? Adjust the whiteness of an image. So we do have this one. Let's start from here. So this is debayer 2. So every time we're going from row. So after we've done the debayer, let's do before we encode the image, let's do a correction white balance, and then 1.4, and then 1.3, and then boom. And then after we do 1.4 and 1.3, let's do a white balance correction, and then we'll call this stage white balance. Stage white, fine. Right, stage white, okay, that's stage white, okay. So we've done stage white. Stage white. Amazing. So let's go back and look at our image. So now, remember, we started with a gray image, and then we did a demosaic on the image, and that adjusted our image to this. And then now we've just done the white balance, so that we see the whites are not really white. They're not really true white. So let's kind of try and adjust the whites. And all of this is, I'm sort of doing a speed run through this. What you'll end up doing is you will experiment with these values. You'll experiment with these values. It's almost like using a volume note. Is this too loud? Is this too low? Is this too loud? Is this too low? And it all depends on what you end up getting. Okay, so let's see. I'm just checking that my audio is fine. Okay, cool. And checking for any questions. Let's see what the white balance adjustment is. Huh? Which one's this? Wow. Okay, cool. So it's kind of whiter, but no, what I want. This looks the same. I might have made a mistake. Ha, you see, stage white. I basically used the wrong input. Cool. So, yeah, amazing. So let's start. So if we start with the start one, we get the gray image, and then the next one gives us the mosaic image, and then we adjust the white balance a little, and now we're sort of starting to see um, basically basically uh, what do we call it? Basically an image, an image of sudden how do I say it? An image of a certain size. Let's actually, I think, let's increase that white balance to 1.5 before we go on. Just max it out a bit, max it out a bit, and then maybe even do a debayer. No, we can still go with debayer. So let's do that 1.5, 1.5, boom, and then let's do that stage right, stage right. Yeah, let's override that so that we get a sharper image change, basically. Okay, cool. So yeah, that's just debayered. and just now this, as you can see, the whites are becoming more white, basically. Now the next part we want to do is basically, um, if you notice, there's, I think this is a black cap here, and this color chart has a black around it. And what you, if you notice, our blacks are not as black as they could be. They're sort of like a little gray. So what we can do is also something called a black correction. So we can do a black correction and see if we can get the black level in the right place. So we have a white balance, and then on top of that, we're going to add a black correction. So, so we do correction, correction, black level, and then let's add something huge like 40, and then let's call this stage black. Okay, let's call that stage black. First of all, yeah, let me do this so you can see stage black. That overrides. Okay, cool. So we've added a black correction now. And then let's go back into here and then add our stage black. Excuse me. Sorry for headphone users. Stage black and then stage black. Let's look at what that gives us. So recall again, as always, we start from the gray image. We debayer that image, we get this image, and then after we debayer the image, what? Wait, no, no, no. We debayer the image, we get this one. Then after the debayer, we get this white one. And then after that one, we get a black. So as you can see, the blacks are sort of more black. But now, basically, what is happening is we have we have how do I say it? Our image is still sort of like lost. And what we need to do is we need to do a few more corrections so that the the how do I say it? The we can start getting the features in the image that we want. And I think if I'm not wrong, if I'm not wrong, I think I added was it a sharpness? Was it where I find it? Just a moment. That's all of yesterday. Okay. Uh, mm, mm. So I'm using a debate 3. My white balance is fine. Mm, mm. Okay, let's go back to debate 3 then. So to debate DB3. Let's do a debate 3 and then we'll see what happens there. Black level, white level. Cool. Probably I did a, yeah, that's fine. I'm okay with the black level of 40. I can also just go with a 10. And then let's do that. And then from here, let's do db3, db3, db3. And let's look at the result. Yeah, so see, now this is starting to look more, more like, how do I say it? This is starting to look more like an image that we can consume, because now we're starting to see real colors in the image. We're starting to see real, we're starting to see, sorry, we're starting to see real colors in image. We're starting to see actual features of the image. And what we want to do is kind of, now what we are doing, basically, I think, what we're doing is we're adjusting through this image. And as we're adjusting through this image, we're starting to build an image that is um, consumable, if I might say, okay, consumable by some end process. And sorry, I was looking at the email. I'm sorry. So okay, cool. Here it is. So basically, what have we done? What we've done this morning is kind of walk through what an image signal processor does. How you go from raw input from a camera, and then how you use that raw input in a camera and you build up. You use that raw input in a camera and you now construct. You're getting just this byte from a camera. And how do you construct those bytes into an image that you can actually observe, or an image that your computer, an image viewer in your computer can open, and then for that you can actually perceive correctly. Okay, but because it's really simple. If we use the wrong settings, and I'll do something here. I'll go something like, let's read this as um, 200. Okay, and I don't even wanna, I don't need to debate it. I don't need to do anything. Let's just go straight back to gray, and I'll show you. So stage gray. Let's do that. Convert RGB 24. Yeah. Okay. So there's let's LS stage gray. Okay. If I bump gray, and we say stage gray PNG, and then basically, and if we go back to our files and we open this stage gray.png, what you'll realize is we will have corrupted the image. We will have read the, see, this is what you get if your parameters are sort of off. We've now consumed the image in a way that is not really, um, that doesn't match what the camera is producing, that doesn't match the pixel array that we have. So what an image signal processor does is you break down and you consume this data in ways that can result in an image that someone can actually look at and consume. And basically that takes us full circle, and it brings us to the introduction of something called libmpix. So which is going, it's in the description, it's going to be in the description, and here's the documentation. And what libmpix does is you have this is a signal processing library that works with the analog signals that come from a sensor, and does some digital signal processing, and then produces an artifact that we can observe. And basically, this is you can libmpix is available on POSIX, which means the computer that you're using. But it's also it's also built so that it works on, I think we consume something like uh, it can produce something like 1 megabit of data using 5 KB of RAM. Basically, it just needs 5 KB of RAM to run, which means you can run this on your microcontroller. Okay. And what we want to we can further improve this so that it runs on single instruction multiple data assembler. And once we can do that, then it's going to be something that is fast enough to like rival other such libraries. And the Linux has quite a few of this. So there's libcamera. So there's libcamera. Libcamera is also an image processing library, but libcamera assumes that you have already done your image processing, or rather, you can give it image processing function, and it will just call it, which is typical of Linux. So libcamera is sort of sits one level higher. You give it you implement image processing functions, and then you can use it to call this image processing functions. Yes, you implement image processing functions, and then you can use it to call those processing functions. And then from that, you can basically, libcamera will connect you to whatever camera you have on Linux, to whatever screen you have, and then it will do all the in-between stuff. And then I think we have something like FFmpeg. Now, I wouldn't say if FFmpeg is a image processor, but it's sort of an encoder decoder. So it works at the end um, um, of of um, of your image processing. At the end, it will augment the packets that you have into something that you can see later. And then I think it used to be V4L2. V4L2. This is video for Linux, and I think this is also this is it's a video driver for Linux, but the beginning of doing video driving is consuming the data that is coming from video sensors or camera sensors and making them into frames, and then from frames you make them into you play a lot of frames per second, you make a video basically. And this is one of those sort of kind of applications. And so those are examples of other image processing applications. And of course, there's a lot of proprietary ones, and quite a few times you'll find that uh, camera sensors will come with image signal processing in the sensor. Like it will be implemented as hardware, and it can do that in the processor. And then some systems, let's say like an iPhone, has such complicated or advanced image processing that you will find that they have an image signal processor on the sensor, and then on top of that they have some more software functionality to apply more images. That way you can do all of the saturation, blurring, you can you can do exposure, you can do white balance, you can do black balance, you can do gamma adjustment, and all of those things that you can do to an image. And basically, all of those the things that you can do to an image is just you're basically applying digital signal processing uh, formulas or statistics. You're applying statistic formulas to uh, a bunch of bytes and producing an image and colors with that. Well, so what really is it that I'm working on? So at the moment, I'm working on introducing color correction functionality. So this is the issue I'm working on. I'm adding a color correction functionality to libmpix. And how this works is you go through the color, you have a color correction matrix. Rather, you have some parameters from the camera manufacturer. You can also discover this by yourself. You can measure them by yourself. And then you go through the pixels generated by an image, and you adjust each pixel according to this color correction matrix. And you do this because uh, the way a camera sees and the way your eye perceives is two different ways of perception. So cameras usually perceive things as they are in the world, and then our eyes perceive things as we have evolved to perceive them. So what you need to do usually is you need to adjust colors in an image, such as this one. You need to adjust the colors in an image, such as this one, uh, such as this one, so that they match up to what the eye expects it to be, and then this can be real colors out there. And basically, if you if you do this if you do this as if you manage to do this as how do I say, if you manage to do this as as best as possible, what you end up with is basically how do I say it? What you what you end up with is an image that is observable and is consumable by the human. And what you would end up with is something like uh, um, let me see if I can check one of the. Mm, do I have a document? Um, Where is this image? Do I have a sample of one that I've made that looks this document? Document. This is a sharpened. Cool. This, you see. So this is an image. This is the same image that we're looking at, with the colors adjusted well enough that you can see all these other colors and you can consume them in. Like now, this is this image and this image. Uh, let's say they're the same image. These are two of the same images, but we've applied different color correction. We've applied different image signal processing functions. And one of the images is observable while the other one is not consumable, basically. And this is an introduction into image signal processing with libmpix. Um, Thank you so much for hanging out with me today. This has been an amazing talk, and a challenging one as well, because it has challenged my understanding of what is happening and how it's happening. And I think it's always good to do this so that we can, relate and see about learning. Well, thank you so much. That's been amazing. And let me see if there are any questions. Is there any questions? No questions. No chats at the moment. Um, yeah. So thank you for coming. Leave any questions you have in the description below, and then we'll check out and see what we understand with you. Thank you. Cheers.